Just a few announcements before we get going. Please I ask that you take a moment to check that your mobile phones and any other technical devices are off or on silent. And can I also remind you not to leave bags or personal items unattended at any time. In the event of a fire, the alarm will go off and we'll leave the meeting room by the emergency exits, so the two at the front and at the back, where we'll be go to Stories Gate outside. In the event of any other emergency, we'll be informed by a member of staff who will provide further instructions. So now to introduce our speaker for this evening. So Dr. Benoit Jones is Managing Director of InBye Engineering, a startup company focusing on technology for the tunnelling industry. He was Course Director for the MSc in Tunnelling and Underground Space at the University of Warwick, and he has worked for OTB Engineering, Morgan Sindall and Mott MacDonald on site and in the design office. Benoit enjoys writing and has written several journal papers, one of which was awarded the IC Telford Premium Award for outstanding contribution to the civil engineering literature in 2009, as well as many articles and conference papers, including 30 consecutive articles in Tunnelling Journal. He's an honorary fellow at the University of Warwick, a chartered member of the ICE and an active member of the BTS, being on the organising committee for the last 3 BTS conferences, and he was also on the BTS WAM committee in its first year of operation. So thank you very much for joining us tonight, Benoit, if you'd like to take to the stage.
Good, good. Okay, let's put the clicker. Right, so I'm going to be talking about strength monitoring using thermal imaging, also known as SMUTI. So I'll talk about how does it work, why we should use it, what's been done so far, and where we're going in the future with it. Here's a picture on the right of a typical batching plant. This one's on the Oberau tunnel in Germany. And, you know, we batch up shotcrete. It's pretty similar to concrete. And if everyone goes away from today with either knowing anew something or remembering something you used to know but didn't quite remember, it's this. And it's if the concrete temperature is 20 degrees rather than 10 degrees, the rate of strength gain is double. And if you go from 20 degrees to 30 degrees, the rate of strength gain doubles. And if you go from 30 degrees to 40 degrees, the rate of strength gain doubles. So, you know, how much faster is concrete gaining strength when you go from 10 degrees to 40 degrees? Anyone? 2 times 2 times 2, 8 times faster. So concrete hydration and the rate that it gains strength is incredibly dependent on the temperature of the concrete. It's the most important variable in concrete. So here's an example. These are isothermal tests. So the specimens of cement paste in this case have been kept at constant temperatures of 10, 20, 30, 40 degrees. Along the x-axis, you've got degree of hydration, which is a measure of how much of the chemical reactions between cement and water that have occurred. So it goes from 0 to 1. Most concretes never get to 1 because it's virtually impossible for all the cement to hydrate. And on the y-axis, you've got the rate of hydration. So that's the rate at which the chemical reactions are occurring. And you can see that the rate is doubling. And it's doubling pretty much consistently across the whole of the hydration. And that's a really sort of valuable property. Because if you were to kind of find a relationship that takes account of temperature, you could make all those curves line up and have one characteristic curve. So we'll be doing that later. So this also shows how degree of hydration increases with time at different temperatures. So going from right to left, you're increasing in temperature. And this kind of shows, actually, you need to notice it's a typical sort of S-shaped curve. is one thing. But also, if you were to find some sort of formulation that took account of some kind of equivalent time, you could make all those curves line up. So if you know the temperature history over time, you can kind of integrate it to find the current degree of hydration. And people have been making use of this since the 1950s to kind of measure the maturity of concrete. One thing to notice is that around about sort of several hundred hours, the curves actually cross over. So this idea of things, of being able to take account of temperature and it works fine, doesn't quite work in the very mature ages. And that's because actually crystal formation is slightly affected by the actual temperature. So this is a typical strength development curve for concrete. So you start off with fresh concrete, it's got no strength at all. And at some point, it sets and begins to gain strength, initially slowly. But actually, reactions between cement and water are occurring before that point. It's just not enough of them have occurred for there to be a sort of rigid skeleton within the matrix of the cement paste. So at some point, enough chemical reactions have occurred for it to start gaining strength. And you can see it starts off slowly, and that's because it's still in a kind of dormant period where the concrete is kind of asleep and there's not a lot happening, and then it ramps up. So another very useful thing, because we saw that the shape of the strength development and the degree of hydration development are both S-shaped, and that means that there's a linear relationship between strength on the y-axis here and degree of hydration on the x-axis. And you can see that a certain amount of hydration has to occur before it starts to gain strength, and that's called the critical degree of hydration. And that can be anywhere between about 0.05 and 0.08, so between 5 and 8% of the reactions have to occur before it starts to gain strength. So how do we model these hydration reactions? And in the old days, you used to use sort of equivalent time and all sorts of strange formulations, but in the last sort of 30 or so years, the Arrhenius Equation has pretty much dominated how we do this. And this says that on the left-hand side, you've got the rate of hydration, so the squiggle symbol, I always forget the Greek name for it, but anyway, that's degree of hydration. So you've got rate of hydration is equal to the normalized affinity, the A tilde, which is itself a function of degree of hydration, multiplied by E to the power of minus the activation energy, EA, divided by R, which is the ideal gas constant, which is universal constant, you look it up, and T is the temperature. So if we know the normalized affinity and how that varies with degree of hydration, and if we know the activation energy, which is the small amount of energy you need for a chemical reaction to occur, and if we also know the temperature at any time, then we can calculate the rate of hydration. So for any given concrete mix, the rate of hydration at any time is dependent only on temperature and the degree of hydration we're at. So if we know the temperature history from the beginning, we can step through time, and in each time step we're calculating the rate of hydration and then calculating the new degree of hydration at the end of the time step and then going to the next time step. And so you can do a time stepping algorithm. So how we get the activation energy and normalized affinities, we can do isothermal calorimetry, where small samples of either cement paste or mortar are put into the isothermal calorimeter, and they're kept at a constant temperature, and it measures how much heat has to be taken out of the samples to keep them at constant temperature. Because it's an exothermic reaction, you need a little bit of energy to make each chemical reaction occur, but when they happen, they give off even more energy. So when on the left, you can see this plot, which is tests at different temperatures, and basically the gradient of it gives us the activation energy. And on the right, you've got the normalized affinity, which is a function of degree of hydration. So the big sort of spike at the beginning is the, in this case, the accelerator reaction. So that, if the normalized affinity is very high, then that means it's really easy for chemical reactions to occur. It's kind of like the potential difference or voltage of chemical reactions, as an analogy. So the higher it is, the more easy it is for reactions to occur. So you have this accelerator reaction, and then you still, even with an accelerated concrete, you still have a bit of a dormant period, and then you've got this long, lower peak, which is the main silicate reaction of the cement. And that's where most of the strength is happening. So shotcrete. So we know how we can do some lab tests on a concrete and work out how it's going to hydrate and what its degree of hydration will be based on some sort of temperature history. But how do we relate that to shotcrete? What can we do with it? So first, some context about shotcrete. This is sort of current UK best practice, perhaps. And it's the use of exclusion zones. So we've got at the front a red zone where no one is allowed to enter. And then we've got a yellow zone where certain people can be there, such as the engineer and the nozzleman, for example. There might be other people as well. And the green zone where anyone who's authorized to be in the tunnel can be in the green zone. So we've got these three zones. And the idea is that you don't release the exclusion zone until you're fairly sure the shotcrete's not going to fall down. And the two main risks associated with the use of shotcrete in tunneling is one, shotcrete falling down, and two is overstressing the lining, leading to collapse of the tunnel. And we don't often worry about that one, but we should. So the status quo, how do we sort of mitigate this risk is we if I go back, we tend to, when we finish spraying the tunnel lining, we pull the machine back into the yellow zone or beyond, and we spray a panel, and then we do tests, usually penetrometer tests, and then possibly also Hilti tests in the panel to tell us what the strength is. So there's a variety of problems with these tests. One is that they're very local. You're only testing really small volumes of shotcrete, so they're kind of the heterogeneity of the shotcrete itself is quite important. And for instance, the penetrometer, if you hit a largish bit of aggregate early on in pushing it in, it will obviously have an effect. The penetrometer, it's quite a big thing. It's probably that big, and you need to apply quite a lot of force to push it in quite a small distance. It's quite hard to know whether you've gone that distance, especially when the surface of the shotcrete's bumpy. You need to be quite a heavy person to even get it to 0.7 or 0.8 MPa. To measure anything above that is not really possible. And then you've got Hilti pull-out tests where you fire 10 nails into the shotcrete and you use that little jig to pull them out. So you measure the penetration distance, you pull them out. There's a lot of possible things that can go wrong with this test. For instance, at higher strengths, you're meant to use shorter nails. And if you use the longer ones, they're not always straight, and then that can actually cause a false reading. And also, you're kind of relying on the engineer doing the tests and reporting them accurately. There's also limited space on a panel, depending on the size of your panel. So you can't just keep doing these tests. And the Hilti pull-out test, to fire 10 nails and pull them all out, takes like 15 minutes at least. So you can't just be continually doing these till you get to the strength you need. You kind of have to make decisions about how long to wait, how often to do them. And they might not be representative of the lining itself. And they might put the operator at risk. I mean, I've put that in because basically I'm thinking if you wanted to test the actual lining, it would put the operator at risk. And that's what we used to do. We used to just go up to lining and do tests in the lining. But also, there are risks inherent in using this equipment. You've got explosive cartridges, you're firing nails, lots of potential accidents, I suppose. You've also, they're destructive tests to some degree on a very small scale, not if you're doing them in a panel that you're going to throw away, but if you're doing them in the lining. And they have quite poor repeatability. I mean, even with a very good operator, you're talking plus or minus 30% kind of repeatability. So looking more in detail on Shotcrete falls, Mike King and others wrote a paper in 2016 about a study of all Shotcrete fallouts on Crossrail, and the majority occurred during spraying or within 15 minutes of completion of spraying, but there was some incidents of fallouts occurring up to 2 hours later, and they listed the main causes: high spraying rates in the crown, building up layers too quickly, unfavourable geometry, like filling localized overbreak, planes of weakness due to trapped rebound, laminations caused by pulsation, that's when, differences in concrete flow due to the pump, or the presence of reinforcement. So, in a sense, a mesh reinforcement, particularly if it's quite a heavy mesh or spar reinforcements, can cause there to be a plane of weakness. So although they might help hold back the shotcrete behind, the shotcrete inside it is more likely to fall down. There's also, another one is striking young sprayed concrete with the excavator. And you could bracket all those as sort of workmanship. They're all workmanship issues. They can all should be dealt with through good shotcrete mix design, training, competence, and all that, and good workmanship of the guys on site. And there's another possible cause of fallouts is insufficient strength gain. And if things like high spraying rates in the crown or building up layers too quickly, I mean, obviously, if you slow down your spraying or you make sure you build up layers more evenly and you don't just do the crown at the end and do the full thickness all in one go, then, in all these cases, having good strength gain is going to be helpful. I mean, even if you've got quality problems like voids or planes of weakness in your shotcrete, if it's stronger, it's less likely to fall down. So, although workmanship issues have to be tackled, knowing what the strength is does give you some measure of mitigation of risk. So what we tend to do is we measure the strength and we hope that we've done the workmanship well. So the other risk, overstressing the lining, and this comes about because shotcrete, obviously, when you first spray it, has very little strength. So we excavate, we spray a sealing layer maybe, and then we spray a primary lining. And then the next thing we do after we've done that is to start excavating the following advance. And as soon as you start excavating the following advance, you get front to back arching of the ground and you start loading very lightly at first, that ring of shotcrete. And then as you continue to advance beyond that point, more and more load comes onto the shotcrete lining. And this has been proven by measurements of stress and numerical modelling and all sorts of things. So you need that, you need the strength of the shotcrete to increase at a better rate than the stress is increasing. So the important factors are the rate of advance, the rate of sprayed concrete strength gain, and the ground behaviour. Because the ground behaviour will affect, how much ground load the lining experiences and how quickly it comes on. So they're the two main reasons why we want to measure strength. So we know how to we know how to do lab tests and get these parameters so that we can say what the degree of hydration of shotcrete is based on a temperature history. But how can we get that temperature history? And like the title of the presentation gave it away, but you could use thermocouples or thermistors like either embedded in the shotcrete or mounted on a surface to measure temperature. But the problem there is you have to install them. You have to go into that red zone and install them, and that's just not allowed. Also, you would be getting a very local measurement, and really what you want is to measure everywhere. So the answer is thermal imaging, of course. With a thermal imaging camera, you can measure the temperature of the surface of the concrete pretty accurately from a safe distance. And you can scan the whole lining without getting in the way of construction operations. So here's a look at some shotcrete, and this is what it looks like in a thermal imaging camera. And you can even, using the built-in software on the camera itself, you can select areas and get average temperatures of areas, and that's probably better than taking point measurements, because point measurements you might be susceptible to something sticking out from the shotcrete that has a lower temperature, for example. And here's another view, a picture-in-picture view. So you can see the sort of richer information you get by looking in this different part of the light spectrum. And here's a video, just shows you a bit more what you can see through the camera. So the cameras always have a little screen on them, and you can see what you're looking at straight away. So here we're sort of actually on a sort of platform in a shaft, which is why you're so high up in the tunnel, and sort of looking down on it. And you can see the recently sprayed bit of top heading there, and this recently sprayed bit of bench are brighter and redder, so they're hotter. And here's a picture of actual spraying. So this is spraying of that right-hand bench bit. And you can see the stream of shotcrete from the nozzle is about 20 degrees, which is typical for fresh concrete batched on site, in London, any time of year really. And pretty soon after the shotcrete hits the wall, it's already going yellow, which means it's going up a few degrees. And here's it after spraying, and you can see at the end of the spraying, I think they just turned off the accelerator just a second before the concrete, and they got a little patch of unaccelerated concrete there, which is showing up blue, that little round blue bit in the middle. And that's not just unaccelerated, it's retarded, so that's not going off for hours. But it's probably very superficial, I wouldn't worry about it. And it's down there, so it's not going to fall anywhere. But those of us who've done a lot of Hilti nail tests know that bit where you try to shoot a nail in and it just goes splat and you get a face full of shotcrete. No? Never had that? Oh, okay, just me. That's why you wear goggles. Keep your mouth closed. So, yeah, moving on. So we can use a thermal imaging camera, get a temperature history, calculate degree of hydration. But we need to relate that to strength. With in situ concrete, that's really easy. You just cast some cubes and crush them at different times. But with shotcrete, you can't really do that. You can't really spray shotcrete into a cube mold. You can't mix it by hand fast enough in the lab, even with mortar, and then you get the wrong strength because it's not as compact as the actual shotcrete. So we have to actually spray at full scale into panels to get shotcrete. So what we do is we spray some panels, we do in situ tests, and we also do thermal imaging, and we plot the strength against the degree of hydration, and we get a linear relationship. So now we've got all the parameters we need for our software, and we can plug them all in, and then from a temperature history, we can say what the strength is. So this is an example of calibration we did at Bond Street Station Upgrade. So there were 3 sets of 4 panels. I'm saying all the testing here was done by Vish Ahuja, so he's a PhD student at Warwick University. Yeah, so he's very careful. So this is really the best kind of possible measurements you can get on site, I think. So here we've got the 3 sets of 4 panels, and the smooth lines are the SMUTI, and the individual points are from penetrometer, Hilti pull-out tests, and also coring at later ages. And we've gone up to 50 or 60 hours, and it's pretty good agreement, but you can see how much scatter there is in the results from the strength tests. And if you look, for example, at that one on the top right, and you look at the triangles, you can see that the scatter is random. It goes one side, then the other. It's not like one panel is always one side of the curve and another one's always the other side. It's just random. So it's all to do with the repeatability of the strength tests. So all we can do is try and go down the middle. We need better strength tests, really. So once we've got our calibration software's all set up, then we do training, and then the guys on site are ready to use it. So usually they would do it at 5 locations around a top heading. So the left axis, left shoulder, crown, right axis, and right shoulder. But it's quite easy in the software to just add points if you've got other areas that you're concerned about, or you don't want to follow that typical pattern, or you want to add a panel, because it's quite useful to, anytime a panel is sprayed, to also do SMUTI on it so that you can check the calibration. So at Bond Street, they also used the total station to define where the monitoring locations were, and this kind of helped them to always take readings back in the same place. So the software is quite nice, I think. When we do the training, it's like literally me talking like this for an hour and a half about the theoretical background, which I love doing. But the actual bit where we talk about how to use the software takes 5 minutes. Not even that, because it's just so obvious and easy. And every time you go into it, you've got your unique login. It knows who you are, and it knows who's added what data. It also knows who's edited what data, knows who's deleted what data, and it doesn't delete anything, actually. It just marks it as deleted on the server. So if someone makes a mistake, you can always retrieve the mistake. So it's very robust in that sense. And it's backed up all the time. So every time you go in with your login, you're taken back to the last advance that you did. So you don't have to drill down through all the menus. And this is just scrolling down that same screen, you just enter the date and time and the temperature. And there's a little thing you can click, and you get like a little calendar thing and a time thing if you want to do it that way, rather than typing it in. And it defaults to the current date and time and temperature. So this is based on a server, which means that you can access it through a browser on any device. So any operating system, any kind of device, you can access the software, as long as you've got a login. And that means it's very secure. It means no one can mess about and change things. If it was a spreadsheet, you'd worry that there might be corrupted versions around the place, and they could, go around the world 10 times before you knew what you were doing. So it just means we've got complete quality control, and it also means you can access the data from anywhere. So anyone, anywhere in the world can access the data if they've got a login. So up to now, it works well when we've got Wi-Fi in the tunnel, but if we don't have Wi-Fi in the tunnel, you can't put the results in straight away. You have to come out of the tunnel to your office and do it. So we're developing an offline app that will be ready in 2 or 3 weeks, actually, that will mean you can actually do the calculation in the tunnel using the software, even if you don't have internet connection. So here's some typical results. Got some, and there's some in situ tests there as well. And here's some more. In this case, we've got on the left is the strength versus age, And the X's are the penetrometer results in the panel, but then the circles later on are actual Hilti pull-out tests in the lining. And then we've got the smooth line is SMUTI on the panel, and the dashed dot line is SMUTI on the lining. And you can see the lining has gained strength much more quickly, and that's because if you look on the right, the temperature history is different for the lining, and the temperature is warmer. And I should note, while we're talking about temperature, that we're measuring the surface temperature, and actually it's probably within the thickness of the shotcrete, it's probably warmer than it is on the surface, because the surface is cooled by the air. But even so, we typically get to peak temperatures of 40, 50 degrees quite often, even on the surface. So it's quite a big change in temperature we're measuring. I think that just sort of proves what's going on. If we focus here at the beginning of here, and this is the worst example I could find, but this just shows the penetrometer results against the SMUTI results. And very early on, you can see the penetrometer is reading higher or giving higher results than SMUTI. And that's partly because on this job we had this was May last year, so we had quite conservative assumptions about the initial strength provided by the accelerator and the initial degree of hydration and things like that. So we were being quite conservative with the SMUTI. But the penetrometer, when you accelerate concrete, it's the accelerators we use are mostly aluminium sulfate, and that reacts with aluminates in the cement and creates ettringite. And the ettringite crystals consume a large amount of water. There's something, I think it's 32 H2O in every molecule of ettringite. So it basically creates a massive drying out of the concrete. So what you've got actually is a very well compacted and low slump concrete that you're trying to push a needle into. And even if it's got zero strength, it will read something because of the friction. You're trying to push a needle into a granular material that's quite compact. So I think the penetrometer might be over-reading. But also, you see later on the effect of the penetrometer reaching its maximum limit. You can't really take a reading more than 0.7, 0.8. And just because we were, trying to take as many readings as possible, we carried on with it. But really, I think you can ignore most of the later ones. And I'll sort of show the next slide sort of proves why to some degree. If you plot all the data of strength against degree of hydration, you see that those later penetrometer results would have to, you would have to jump from below 1 MPa up to about 2.5 with no increase in degree of hydration or time, and when you get the first Hilti pull-out tests. And so it doesn't really make sense. So I'm pretty sure we've got a lot of problems with the penetrometer, really, so is the answer. So I'll just talk briefly about another project. It's quite exciting. So this is in Germany, and this is we've been working on it since September, and this is with InBye Engineering's sort of partner company called Matrix Engineering, who are based in Munich. And this is a 3-kilometer bypass tunnel of the small town of Oberau, and it's in Bavaria near the Austrian border. So it's very scenic, very nice place to visit. So it's 2 bores, 2 lanes in each bore, so quite a big tunnel. And it's sort of a typical alpine tunnel job. So, beautiful blue skies and mountains, and drill and blast, and thin layers of shotcrete, like 100 millimeters or so shotcrete. Here they've got mesh, but they haven't got it everywhere. It's just this is a particularly bad bit of ground. And it's basically the shotcrete is just temporary, and afterwards they put in waterproof membrane and in situ concrete. So they're not too worried about the lasting, permanent quality of shotcrete in the same way as people familiar with London projects would be. This is the calibration. And this just shows, we've got a lot of data, but I just wanted to show the sort of extremes. So we've got groundwater inflow in a lot of places, and the groundwater is something like 12 degrees. So actually where that's running down the face of the shotcrete, it's actually cooling it down, and the shotcrete's not very thick. So got one example there, the dashed line, which is pretty much bumbling around sort of low 20s. So even though it's producing heat from its hydration, the groundwater is taking it away. And then we've got the solid line, which is somewhere with no groundwater flow, and it's going up to nearly 50 degrees. And on the right, you can see the strength gain curves, and they're very different. Although at the start, they're not too different, and that's partly because the temperatures aren't so different then. And also you can see the sort of, the initial part of the strength gain is a little bit different to Bond Street. We've got a bit more early strength, and that's basically because they've got 9% accelerator. It's quite heavily dosed with accelerator. So I'm just going to just talk a little bit before we go to sort of some conclusions about some sort of typical things that have been asked about it. And the first one is it essential or is it a nice to have? And I hope you'll all agree, because it's quick, safe, and easy to use. It's as easy as taking a photo, really. And tapping results into computer. It's very simple. It's sort of holistic rather than local. So we can actually scan the whole lining, and we can take continuous measurements. There's no cost to taking as many measurements as you like. You just have to be there, and it takes seconds. And the data we get is reliable, it's repeatable, it's traceable, accessible from anywhere, and it's richer in information. So I think with all that, is it reasonably practicable to use it? I would say yes. Well, you might say, what about the cost? And I'll be quite honest with you, I have no idea how to price this. I've been developing this for 4 years or so, and I have no idea how much it should cost. And at the moment, so I thought I'd do a bit of market research while you're all here. So if you've got a big major tunnel job, might spend anything from £100,000 a day up to maybe £1 million a day. So that's how much they're burning every day on overheads, people, materials, everything. So how much do you think per month they should spend on something like this that maybe improves safety and quality control? So are you all thinking of a number? How much do you think people would be prepared to pay for that? You all thinking of a number? Whose number is more than £100,000 a month? No, I didn't think anyone would go for that. Whose number is more than £20,000 a month? Yeah, great, a couple. Whose number is more than 10,000 a month? And who's at more than 5,000 a month? Yeah, oh, quite a few. More than 2,000 a month? Yeah, less than 2,000. Nothing at all. 1,000. Oh, okay. Well, the truth is more around the 2,000 mark. And that's based on how much it costs to deliver it all. And I've no idea how much to charge. So anyway, that was useful to me. Thank you. And another thing someone said was, doesn't it give a false sense of security? With this sort of illusion of high-techness and software and whizzy graphics and things, technology. And I kind of think, well, you could say that about any test. Any test you do can give a false sense of security. We as engineers have to understand the limitations of the tests we're using. And, people used to say a lot about numerical modelling, and still do. that it gives the illusion of pinpoint accuracy to 10 decimal places, and it's very dangerous, and you know, everyone should be very careful because it could be completely wrong, but it tells you it's, you know, it gives you the illusion of giving a perfect answer. But I think we still use numerical modelling because it's a really useful tool, and we just realised that we need education and we need to understand its limitations. The final one is, this was a funny one, because someone in a meeting had asked me, will it help with production? Will it speed up production? Because we can make a business case around that. And then the next person to speak was basically saying that current strength tests take ages, and so they slow down the miners, and that's a good thing. And I kind of wanted to say, I was very, you know, obviously polite, but I kind of wanted to say, well, you should be able to control your miners. You know, they shouldn't be excavating the next advance until you say it's okay for them to do so, you know. And, you know, it's all about behaviour and behavioural-based safety and avoiding complacency and making sure everyone's competent and educated. I think our experience at Bond Street Station Upgrade was that the training and the focus on early strength that using SMUTI brought sort of actually improved motivation, improved behaviour, and got everyone thinking more about it. So I think it actually helped with it, if anything. So future challenges. So I'd like to kind of integrate a thermal imaging camera with laser scanning or photogrammetry, because if it was mounted on a laser scanner, for instance, it would know what it's looking at, and therefore it would immediately know the temperature history, and it could calculate the strength. And you could, you know, it already exists that you can get nice 3D views of the profile of a shotcrete, the thickness of a shotcrete. If you could also get the strength of a shotcrete, how amazing would that be? You know, if you in the tunnel could look on your tablet and look at, you know, your tunnel lining and know its age, its strength, everywhere in the tunnel, and its thickness, that would be quite useful. And I say there, you know, possibly even stress. So if you could actually measure convergence accurately enough, you could measure strains or calculate strains and then back calculate stresses. And if you were using it with thermal imaging, that would give you really useful information about actually the maturity of the shotcrete, because all the properties of concrete are correlated to degree of hydration. Age is a really poor measure of maturity. Degree of hydration is the perfect measure of maturity. So all these parameters like strength, stiffness, shrinkage parameters, creep, everything, even coefficient of thermal expansion, everything, are correlated to degree of hydration much better than age. Maybe a European standard for SMUTI, that would be great in the future. If anyone knows how you go about getting one, you know, please talk to me afterwards. And a sustainable business model, because, you know, innovations only work if you've got a good idea, you understand how people will adopt it and integrate it into what they're doing, and you've got a sustainable business model. So I think I've got 1 and 2, but the third one is not quite there yet, but hopefully. Okay, conclusions, and it's important to reiterate this as many times as possible. Shotcrete falls down for many reasons, and monitoring strength gain is not a guarantee it is safe. And that goes for any kind of strength measurements, but it does reduce the risk. So, SMUTI enables remote assessment of strength of a sprayed concrete lining, improving safety and quality control. It's quick, safe, and easy to use. The data is secure, rich in information, accessible and traceable, and the software's intuitive, user-friendly, and even in German if you speak German. So some entrepreneurial stuff. I just thought this might be interesting to some people. Just some things I've kind of worked out the hard way. Your first customer needs to understand innovation and the need to beta test and develop things. So it's really important when trying to develop things like this, your first customer or first couple of customers, that they understand this is going to take a little bit of work, but there's a lot to gain from it. I also say, beware of those who do not value ideas. So if you've got a great idea, be careful who you talk to about it. Talk to people who you know love ideas and want to see yours flourish, and they'll be supportive and they'll give you good advice. And know what your objectives are. Do you need a patent? Patent? Who knows? But patents, they don't cost that much to get, but if you ever wanted to defend it, it would cost you millions to defend it in court if someone wanted to use your technology. I think if there's lots of ways to protect intellectual property, because what you want to do is you want some time to have a go at something and develop it without loads of people just going in all different directions with it. So you want to kind of have that ability. And you can protect it through like just keeping something secret is one way. Loads of stuff I haven't told you. Or just staying ahead of the competition, or having a good reputation, things like that. So there's lots of strategies, and business plans are really important. And there's this great book which I think was written in like the 1980s or something, and it's called Crossing the Chasm, and it's all about the technology adoption life cycle. And I think it's a really useful model. So early on you've got innovators, and they just want to get hold of any new thing and try it out, and what if I plug that into that and see what happens? And they're great because they give you really good feedback, but sometimes they can have a tendency to want to develop things in ways that maybe aren't useful to anyone else in the future, so you need to be careful. Early adopters, they're great because they're just visionaries who want to get ahead. They love new ideas. They want to kind of work with people and get things going. So they're probably a great bet. But then you've got like the early and late majorities, and they're like the big rump of people. And most of them, they want to stick with the herd. And I think most of the construction industry is in that bracket, I think. And there's a big chasm between them. So it's getting enough momentum to then get it to the bulk of people, perhaps. So just thank some people. Vish Ahuja, who's a PhD student at Warwick, he did a lot of the lab tests you saw there, and a lot of the stuff on site as well. Dr. Shuangxin Li, who worked as a research fellow early on when we were sort of doing a feasibility study. Colin Banks, Martin Davis, Roger Thorpe, who work in University of Warwick Labs. Trevor Power at Warwick Ventures, who's kind of given me loads of good business advice. Matrix Engineering in Munich, and the Oberau Tunnel team. Marty is the contractor, in case I didn't mention that. Bond Street Station Upgrade team, and Costain and Langer Rock, and there's a couple of people here. Great to see you. And Whitechapel Crossrail team, BBMV, who've all been very helpful along the way. And so any questions? Oh, and by the way, this is we won 2 tunnelling awards, and also the Austrian Tunnelling Association gave SMUTI an award as well, which was nice. Okay, thanks very much.
Thank you. Okay, so we've got a few microphones in the audience if anyone's got any questions. There we go, all from Anita.
Anita Boyd, London Bridge Associates. Thank you, Benoit, for your presentation. What is your biggest challenge to date?
Should be all right.
The biggest challenge To date, I think probably like since last sort of June, I've been working on this full time, and then it's been like way easier. Before that, I was working full time in university, and it was virtually impossible because I kept wanting to do stuff, and I just never had the time. So I guess it's been a lot easier since then. The biggest challenge, I think, is getting the sustainable business model. It's quite difficult. So I'll last a few more months, but then I'll have to probably get a proper job.
Well done.
Hi, Jiangsu. Just a quick question. I just try to understand how quick will you be able to get the early age shockwave strength. For example, if I spray a big area of primary lining, and I spotted there was one area, say 1 meter times 1 meter, there was with a low temperature, which means underhydrated. And after I noticed that, I keep scanning the temperature every 15 minutes, and then I immediately input that into a laptop with a wireless connection, to the server. How quick will your software to be able to calculate the early age strength of the shockwave?
It's pretty much immediate, yeah. So you can get a result immediately, and you can see it on a graph on the screen now.
So it's basically just according to your theoretical equations, you calculate you have a relationship between temperature and degree of hydration and your shockwave strength. Is that sort of like just to do calculation automatically? I mean, in the software?
So it's kind of like a database of data, and it interpolates between the data points and then just steps through, and it's very quick. I mean, it might have to do 1,000 steps, but it really doesn't take long. It's very quick. Yeah. So there's no delay really to speak of. No.
Just.
Hello, I'm Avantika from LU. I was just wondering, is there any limitation in terms of distance for the SMUTI to work just without any problems?
It depends on the camera you're using. I mean, the one we typically use, I think up to about 10 meters is absolutely fine, but it depends on the lens in the camera. So the further away you are, unless you change the lens, the further away you are, the smaller the kind of is the area you're looking at on the screen, or it just gets more fiddly and difficult to actually get a solid reading. So, but I mean, yeah, 10, 15 meters is very easy. That works fine. But sort of more than 15 meters, it would start, yeah. And also the angle would be weird, and yeah, it would be more difficult. But then you just, if that was really important, you just use a different camera. A more expensive one, probably.
Hi, it's Qingtang Shen from Mount McDonald. You have mentioned about the case in Austria, you have a colder groundwater. So I was thinking it will affect your measurement in terms of temperature. And then how did you calibration this into your equation? For example, I think there may be other issues will affect the temperature actually you measured in relation to the early concrete strength things.
Well, there's loads of different factors that affect temperature. Actually, when I started this with several years ago, I was spending ages trying to work out, Fourier equations for heat flows and Newton's law of cooling and all this. But actually, it doesn't matter, because it's the temperature that matters, and you're measuring the temperature. And although, if you wanted to know what's happening, within the shotcrete or at the back of the shotcrete or something like that, then you would have to do all these calculations. But you're measuring the surface. So basically, we're measuring the surface temperature, and we're estimating the strength of the surface. And in most cases, we're assuming that the shotcrete within the body of the lining will be warmer because it's insulated. So I think that's fair enough. I mean, the other in situ tests we do are all pretty much near the surface as well. So it's similar to that, I suppose. It just makes things way simpler. Otherwise, you have to make loads of assumptions about the thermal conductivity of the shotcrete, of the ground, you know, the temperature of the ground, the airflow. It would get very complicated. Yeah.
So have you found with different thicknesses of lining that it makes any difference, or you get better correlation with thinner or thicker linings?
No, it makes no difference. It's just that if the lining is thicker, it will get warmer. But we're measuring that anyway, and we're taking account of it in the equations. So it's fine. It's all taken care of.
One more down front.
Just an idea. Sorry, Stephen Penfold, retired. I wonder whether it might be more beneficial to tie your imaging to the tensile strength of the concrete rather than compressive strength, because it's the tensile strength where there really is the huge bit of uncertainty. I think most of the existing equations still go back to René Ferret in 1896. So that's how much progress there has been in assessing tensile strength of concrete.
Yeah, and tensile strength at early age might be different.
Yeah, but when you're feeding into most concrete software numerical modelling, you're using some version of Eurocode, and even RILEM at base goes back to Eurocode, and it is this huge area in the tensile strength of the concrete where it Mike didn't say so in his little bits, but it's always the eccentricity of the tunnel or the openings or where the tensile strength of the concrete becomes critical that you get your failure rather than the compressive points.
Yeah, I guess we're just used to using compressive strength as sort of an index for the other parameters in a way. So, I mean, we kind of, yeah, it's an interesting point. It should be like the tensile strength or the shear strength should be just as important. Yeah, I agree.
I'll go for one.
Yeah.
Sam Huckle, Balfour Beatty. I'm trying to think here about how you could get your product out to mass market. So obviously we're Tideway working for the contractor, and there's a big move at the moment to install cameras on plant and make plant movements safer. I'm just thinking if you could perhaps simplify the data that you get to make it into a safety tool. Do you think that's possible?
Well, there's a laser scanner coming out soon that has a built-in thermal imaging camera, so maybe that might be a useful thing to put on some sort of vehicle. I don't know, because it would tell the difference between a plastic bag blowing across in front of you and an actual living thing. But I mean, we just use, at the moment, we're just using an off-the-shelf thermal camera, and there's plenty of other uses you could put it to. I mean,
because I'm guessing you're going to be collecting quite a lot of data, and perhaps you'll be able to correlate that data with actual strengths and be able to perhaps establish go, no-go zones or regions within your data where things are actually safe or not unsafe.
Yeah, I guess. I mean, generally, people assume that the shotcrete's not going to fall down once it's got half an MPa of strength, I think, is just the general kind of way people do it. I mean, technically, if you do the calculations, it should self-support its own weight at probably less than that, but it's hard to be sure you've got penetrometer measurement of 0.25 MPa. But when you got 0.5, you're probably a bit more sure it's okay. Yeah, so I'm not sure where that number comes from. But because it's easier to control. I think it's possibly secondary linings are much more tricky because you're working your way through the tunnel and people might want to access, from both sides, whereas with primary lining, you kind of got the face area, but once it's gained sufficient strength, it's okay, and that's usually behind where you're working. So it's kind of a bit easier to control access, I think. Does that sort of answer it?
Yeah.
Yeah.
Okay. Well, one more at the back.
Yeah, final question. Tom McGowan, Mott McDonald. Thank you very much, Benoit. It was very interesting. I have novice questions on concrete. As far as a hydration reaction and the degree of hydration, can you just make an assumption at the beginning when it's sprayed? Is it a given ratio? And then does the algorithm just keep track of that based off the temperature reactions? Could you clarify that for me?
Not sure what you're asking there.
Okay.
Yeah.
As far as I understood the way that SMUTI works, is it you take a reading of the temperature, and then you also have the degree of hydration at the beginning, and then based off the next temperature, it calculates the change in hydration and also the strength. Perhaps I've misunderstood that.
Yeah, I guess it goes right from the start. So we assume that the end of spraying is the start, but that's quite a conservative assumption, I suppose, because sometimes spraying a lining takes an hour. Yeah, so we then are assuming that the hydration starts there. Does that answer your question? So we're assuming the hydration starts when you spray it.
Okay, I mean, I was probably just asking what hydration was. It's not my background.
Yeah, I think, well, previously we used to make assumptions about the initial degree of hydration because we had trouble doing tests to get the parameters early enough. So we sort of made an assumption about how much degree of hydration was contributed by the accelerator reaction and then started from there. But now we're modeling that in its entirety, really. So we're modeling it right from the start.
Thank you.
And we have one final one down front.
Hi, Pedro Ferreira from University College London. I was just wondering, Benoit, if you have done any study about the emissivity parameter of the fresh concrete and the sort of slightly older concrete, because water is disappearing, or I don't know, solidifying the mass. So I was wondering what happened with the emissivity, because emissivity is one of the biggest parameters, is one of the parameters that actually affects quite a lot the temperature that a thermal camera measures.
The what, sorry? The
emissivity? Emissivity, yes. Because I think in your pictures I saw 0.98, so I think you were using a 0.98 on the camera, or you don't really look at it.
Yeah, I think, well, we typically use 0.95, and that's recommended for concrete. Yeah, I've not looked into whether it's different when it's wetter or drier. I haven't really investigated that. But we have compared it to kind of actual temperature measurements, and it seems accurate enough, I would say.
Yeah, no, it's just that I'm a thermal camera user as well, and what we notice is that you can measure the right temperature of a particular body that has the right emissivity. But the camera, because you are measuring everything around you, if you have different materials, they are likely to have different emissivities. So you probably will be either underestimating or overestimating the temperature in particular cases or in particular areas. Okay. So that might be something that will influence the right measurement of temperature. So, I mean, it's worthwhile to look at it.
Okay.
Okay, great. Thanks very much. Can we just say thank you to Benoit in the usual way? And And then we've just got a few announcements for upcoming events, so hopefully they may appear. Okay, so the next BTS evening meeting is on the 20th of April, and it's the Harding Prize for 2017. So we've got 3 under 35 members of the industry presenting their papers that they've submitted, so please come along and support them, and there's some really interesting topics in there. Next BTSYM workshops on the 18th of May, so we'll be announcing details of that soon. And then the next BTSYM evening meeting is on the 8th of June. Again, will be coming up shortly, but if you've got any suggestions or presentations that you would like to see or workshops held, then please contact Sam. We've got our BTSYM Summer Social on the 2nd of June, so we're going to Flight Club in Bloomsbury, so please come along. All the details will be announced on that shortly. And then the annual dinner, so the BTS annual dinner is coming up on the 5th of May. There's still a few BTSYM half-price tickets left on our tables, so if you're interested, let us know and drop David an email to get the code for that. And then there's the BTS Design and Construction course in July, so from the 3rd to the 7th of July. So for those who don't know, it's a week-long course at University of Warwick. It's always an excellent event, lots of different presenters coming along, presenting on their specialties. And the BTS also offer 5 free student or apprentice places, so the applications for those are open at the minute. So for details of that, again, contact David Brock. Okay. So I think that's it. Hopefully you'll join us in the bar for a drink. Hopefully Benoit will be there to answer any further questions that you have. And thank you very much for coming along tonight.